What if the entire universe around us is just a small part of something far more grandiose? Every evening, on the dark sky, we see a thin, glowing band of light, the Milky Way. But have you ever wondered what lies behind this mysterious glowing strip? It's not just stars. It's billions of worlds floating in the endless ocean of darkness, held together by the invisible force of gravity. Our home in the universe is just one of hundreds of billions of stars, revolving around a mysterious center, where something truly terrifying might be lurking. But what is this creature? And is it true that one day it could awaken? Every corner of the Milky Way is a mystery. Stellar nurseries where new stars are born, regions where old stars meet their end, dark matter that, like an invisible ghost, holds the galaxy in its embrace. But if we know so much, why are there still unanswered questions? And what will happen when the two giants, the Milky Way and Andromeda, collide in a cosmic dance billions of years from now? If you want to learn more about the mysteries of the universe and journeys to the center of our galaxy, subscribe to the channel and like the video so you don't miss the most interesting discoveries. The Milky Way is an extensive collection of cosmic dust, gas, and billions of stars, one of which is our Sun. The name of our galaxy, the Milky Way, originates from ancient Greek and Roman mythology. The ancient Greeks envisioned this band across the sky as a trail of milk left by the goddess Hera. Various peoples of the world saw their own images in this celestial band. For example, East Asian cultures referred to it as the Silver River of the Sky, while Finns and Estonians called it the Bird Path, and in South Africa, it was perceived as the Spine of the Night. The primary structural component of the Milky Way is its disk, which has a flat shape and includes spiral arms. Most of the galaxy's stellar mass, about 50 billion solar masses, is concentrated in this disk. The disk is divided into two main components, the thin and thick disks, each with its characteristics. The thickness of the thick disk is around 1.2 kiloparsecs, while the thin disk's thickness is 400 parsecs. The outer regions of the galaxy are characterized by an increase in the disk's thickness. The thin disk contains younger, metal-rich stars, while the thick disk is dominated by older, low metallicity stars. What is known about the spiral arms of the Milky Way? And if they are hidden from our view by a veil of interstellar dust, what secrets might they conceal behind this cosmic curtain? The spiral arms of the Milky Way are difficult to observe in the optical range due to the absorption of light by interstellar dust. However, they can be detected by the distribution of neutral hydrogen and molecular clouds, as well as by the location of star associations. The density of gas in the spiral arms is several times higher than in other parts of the disk, and it is in these regions that star formation is most active. The spiral arms are density waves that rotate at a different speed from the stars and gas. 4 major spiral arms are identified in the Milky Way: Centaurus, Perseus, Norma, and Sagittarius. What lies within the spiral arms of the Milky Way, beyond visible stars and gas? And how do these regions influence our galaxy? How accurately can we study and map the structure of these arms, and what remains unknown about their internal processes? The Centaurus arm, also known as the Shield or Shield-Centaurus arm, is one of the key galactic arms of our galaxy. Despite its location in a difficult-to-observe region, scientists have managed to gather valuable data on its structure and composition. The Centaurus arm contains many significant astronomical objects, including large star clusters, molecular clouds, and remnants of supernova outbursts. Among the well-known objects in this region is G007.47 plus 00.05. G007.47 plus 00.05 is a natural source of coherent, in-phase radiation, a cosmic maser. Maser signals appear bright and are easily detected by radio telescopes due to the properties of the medium. Astronomers from the Max Planck Institute for Radio Astronomy and the Harvard-Smithsonian Center for Astrophysics used the Very Long Baseline Array, VLBA, radio interferometer to estimate the distance to the star-forming region, G007.47 plus 00.05. Their measurements showed that the distance to G007.47 plus 00.05, as well as to the outer shield Centaurus arm, is about 66,500 light-years, or 20.4 kiloparsecs. This achievement set a new record for parallax-based measurements, breaking the previous record, which was almost half as small, 36,000 light-years. These objects are important targets for astronomical research, as their observation helps to better understand the processes of star formation and the evolution of stars. Of particular interest is the region where the Centaurus arm connects with the bulge, the central thickening of the Milky Way. This region is rich in star-forming areas. In 2006, astronomers discovered a large star cluster there, known as RSGC-1. It contains 14 red supergiants, massive and bright stars in the later stages of their life cycles. Just a year later, in 2007, another star cluster, RSGC-2, was discovered a few hundred light-years away from RSGC-1. This cluster, containing around 50,000 young stars, is considered one of the youngest in the galaxy, with an age of less than 20 million years. Remarkably, RSGC-2 hosts 26 red supergiants, the largest known group of such stars, making it a focus of attention for astronomers. Besides RSGC-1 and RSGC-2, the Centaurus arm also contains two other significant clusters, RSGC-3 and Alicante-8. RSGC-3 was discovered in 2010 as part of the GLIMPS survey, and its age is estimated to be 24 million years. It contains 16 red supergiants with masses of about 12, 15 times that of the Sun, which are progenitors of Type II supernovae. The cluster's total mass is estimated to be 20,000 solar masses, making RSGC-3 one of the most massive in the Milky Way. Further studies have uncovered at least 30 more red supergiants in the vicinity. This region also possesses quite remarkable astronomical properties. Alicante-8 was discovered in 2010 as part of the 2-mass survey. At the time of its discovery, only 13 red supergiants were identified in the cluster. It is located in the constellation of the Shield, about 23,000 light-years, 6 and 7 kpc, from the Sun. It is believed to be located at the intersection of the northern edge of the long bar and the inner part of the arm. The age of Alicante-8 is estimated to be 20 million years, and its mass is between 10,000 and 20,000 solar masses, making it one of the most massive open clusters in the galaxy. These objects increase interest in the region, which, despite its observational challenges, continues to yield valuable discoveries. What secrets does the Perseus arm hold? What mysteries and new findings has it helped to uncover? The Perseus arm is one of the key spiral arms of the Milky Way, located more than 13,000 light-years from the Sun. Its radius is about 10,700 parsecs, making it one of the longest and most noticeable structures in our galaxy. For a long time, it was thought that this arm had a clear and narrow shape similar to other spiral arms. However, a 2022 study challenged these established views of the structure. Previously, it was believed that the Perseus arm represented a clearly defined spiral, but a study led by J. Pike opened a new perspective. Scientists found that part of the arm beyond the galactic orbit of the Sun might be illusory. This suggests that its supposed shape could have been mistakenly interpreted. The basis for this illusion is a phenomenon described by W. Burton in 1971. According to his hypothesis, the visible structures of arms might be the result of complex interactions of material density and radial velocities, rather than existing as solid objects. To test this hypothesis, J. Pike and his team used a new method for analyzing distances to cosmic objects. They compared data on the reddening of interstellar dust with distances determined by radial velocities of objects in the Milky Way. This approach allowed for more accurate determination of the positions of dust clouds that were previously thought to be part of the Perseus arm. It turned out that many of these clouds were not located on the assumed arm line, but were distributed up to 10,000 light-years away, forming scattered fragments. These results prompt a reconsideration of approaches to modeling the spiral structure of the Milky Way and fundamentally change our understanding of galaxy structure. The Norma arm is one of the smaller spiral arms of the Milky Way. It starts about 2.2 kiloparsecs from the center of the galaxy and stretches up to distances of about 15.5 plus 2.8 kpc. This extent encompasses both the inner and outer regions of the Milky Way. Within these bounds, the arm interacts with other spiral structures, making it difficult to precisely determine its extent and boundaries. The Sagittarius arm lies between the Centaurus arm and the Orion arm, and it is named after the stars of the Sagittarius constellation located nearby. The distance from the Sun to this arm is about 1.8 kpc, approximately 6,000 light-years. The Sagittarius arm is divided into two parts. The outer curved part, located near the central bar of the galaxy, is called the Sagittarius arm, while it lies within the constellation Sagittarius. As it moves into the constellation Keel, this part is referred to as the Keel arm. Let's now return to the overall structure. What is the bulge of the Milky Way, its central part, and halo? In the central part of the Milky Way is the bulge, a spheroidal structure measuring 2.2 by 2.9 kiloparsecs. The mass of the bulge, along with the bar, is about 9 billion solar masses. Unlike classical bulges, the bulge of the Milky Way is considered a pseudobulge. It rotates, has a flat shape, and resembles a disk. The bulge contains boxy and disc-like components. Observing stars in the bulge is possible through the barred window, a region of the sky with reduced interstellar absorption. The central region of the Milky Way also contains a bar, an elongated structure about 4 kiloparsecs long. Its axis is tilted at an angle of 20 degrees to the line of sight, creating asymmetry in the visible distribution of stars. The motion of gas in the central part of the galaxy also indicates the presence of the bar, as the radial velocities of the gas reach 200 kilometers per s. Closer to the galactic center, there is a secondary bar with a radius of about 150 parsecs, which is linked to a molecular gas ring with a radius of 200 parsecs. How can stars in the halo, located tens of kiloparsecs away, reveal the secrets of the ancient history of the Milky Way? How do these unique structures affect the dynamics and evolution of our galaxy? The stellar halo is an extended spherical subsystem of the Milky Way, covering an area up to 80 kiloparsecs from the galactic center. Its stellar mass is about 1 billion solar masses, and the most distant stars in the halo have been found at distances up to 320 kiloparsecs. The halo contains a significant amount of dark matter, and within it, stellar streams have been discovered, such as the Sagittarius stream and the Unicorn ring. Stellar streams are groups of stars with similar velocities and chemical compositions that form as a result of tidal disruption of dwarf galaxies within the Milky Way system. The Sagittarius stream includes stars that were torn from a dwarf elliptical galaxy in the Sagittarius constellation due to tidal interactions with the Milky Way. The galaxy is currently merging with the Milky Way, a process that has been ongoing for billions of years. The idea of this stellar stream's existence was proposed in 1995 by astronomer Donald Lynden Bell after analyzing the distribution of globular clusters in the Milky Way. In general, the structure was discovered in 2002 by Newberg and colleagues, as well as in 2003 by Majewski and others, using 2 mass and SDSS survey data. The Unicorn ring is a filamentary ring-shaped chain of stars that wraps around the Milky Way 3 times. This formation is believed to be a moving group of stars torn from the dwarf galaxy in Canis Major, likely during its absorption by our galaxy. However, the existence of this dwarf galaxy is currently disputed. The mass of the ring is about 100 million solar masses, and its extent reaches 200,000 light-years. The Unicorn ring was discovered in 2002 as part of the Sloan Digital Sky Survey. In 2006, using 2 mass data, researchers proposed the hypothesis that the ring could be part of a warped galactic disk of the Milky Way. However, in 2007, observations made at the Anglo-Australian telescope showed that this stellar structure most likely has an extragalactic origin. The Milky Way is a complex and diverse system. Thanks to new observational methods, knowledge about the Milky Way is continuously expanding. These data help to understand how the galaxy formed and evolved over billions of years. What is the significance of the central region of the Milky Way for studying its dynamics? What are the features of the supermassive black hole at the center of the Milky Way, known as Sagittarius A*?